For everyone, this is Lucile Saulnier. I hope I pronounced your name right. Lucile is a machine learning engineer at Hugging Face, and she develops and supports the use of open source tools. She's also actively involved in many of the research projects in the field of NLP, such as a really cool project about collaborative training. So this is where you try to basically train like a transformer from scratch, distributed across multiple machines in the world. So people share their kind of compute for this. It's a really cool project you should check out. We have it on the blog. And she's also heavily involved in the BigScience project, which you may have heard about. This is a 1 year kind of research endeavor to try and train a very large language model that is kind of like GPT-3, but hopefully with a lot more insight into how this model works. And today she's going to explain to us how to get our own tokenizer with Hugging Face Transformers and the Hugging Face Tokenizers libraries. So thanks, Lucile, and we'll see you for the questions.
Hello everyone, I'm really happy to be with you today for the launch of part 2 of our course. What I wanted to propose to you today is to see how you can get your own tokenizer with the Transformers on Tokenizers Hugging Face libraries. What I'm going to say next will be mostly for the purpose of training a language model, but be aware that you can absolutely meet tokenizers in other contexts. So, what is a tokenizer? A tokenizer is a component located between the textual data and the language model. It is in charge of preparing the data, in other words, putting the data in the format expected by the language model. More specifically, a tokenizer is responsible for dividing a text into a sequence of smaller units called tokens. The big point is that this tokenizer is coupled with a vocabulary that maps each token with a unique number. In this way, the tokenizer transforms a raw text into a sequence of numbers. We do that because a language model is a function that can only take numbers as input. The tokenizer is thus really designed and trained to be the best adapted to the data and the language model. And this applies to all the sub-operations included in the tokenizer, from normalization to post-processing. So when you want to train a language model, you will ask yourself the question, what should I do with the tokenizer? The first possibility is that there is already a trained tokenizer that fits your needs very well, and in this case, the question is quickly solved. On the other hand, if you do not find such a tokenizer, you can perhaps find a tokenizer whose design is appropriate to you, but that you will need to adapt to your data. In other words, only to retrain it. Or you perhaps want to completely design your own tokenizer on training in your data. This is the third case, showed here. The good news is that the Hugging Face libraries have put everything in place so that you can do everything, whether you are in the first case, the second case, or the third case. The course that was just released has a very detailed chapter on tokenizers and will allow you to really understand everything about tokenizer and how to get your own tokenizer. So I thought it might be interesting to show you another resource that shows you on a simple example how you could do if you are in the case 2 or 3 just discussed before. This should give you a little bit of an appetizer before you start the course. So I'm going to leave this presentation and move on to the notebook. You may already know them, but you can find in the Transformer repository a series of notebooks that explain concepts or how to perform several tasks. And among them, you can find one called Train New Tokenizer. To save some time, I already or download it to run it locally. A little extra information. The interesting to do it locally. So here you will need to have installed the dataset on Transformers packages with one extra dependency, which is sentence piece. So you can see here that I have everything installed before. Then, whether it's for case 2 or 3 that we just discussed before, you will need to train a tokenizer model. And so for that, you will need some data. If you plan to train a language model afterwards, you just need to take a subpart of your training data. For this example, we will still need data, and we will take the wiki text too. We can load it directly with the dataset library, which allows us to consult it very easily. We can see it's composed of 36,000 text. We can also look at the first example, or even the first 5. What we need next is an iterator on our data. So we are going to do that right now. You can see with this cell that the simple way to do it, but it's not very suitable because it loads everything in memory. So it's better to use the batch iterator method defined just below. We will now see the solution to the situation 2 of earlier. That is to say that you have found a fast tokenizer whose design suits you, but not its training. In this notebook, we will say that the design that suits us is the one of GPT-2. So we load this tokenizer, and we check that it's really a fast tokenizer. And then we just have to use the train new from iterator method to train it again on our data. After it's trained, we can see what it gives on our dataset. And that's all. The new tokenizer is ready, so maybe it's a good idea to save it. And we can even send it directly to the hub to get it from everywhere and share it with other people. So if you want to do that, you just need to run this cell and fill in your Hugging Face credentials. Okay, and you will also need to have Git large file storage installed. So if you don't, you can do it by uncommenting this line. And there you go. You can load it on the hub. After that, very easily, you can check with this line if you can retrieve it. So here it's the case. And that's all. The case 2 is finished. So now we can see how we can do when we really want to make a complete tokenizer from scratch. And for that, we will use the Tokenizers library. For this example, we will remake the tokenizer of Bert, but you can really imagine everything. So to start, we'll initialize a tokenizer with a model of our choice. Bert uses WordPiece, so we will use WordPiece here too. If you remember my little diagram at the beginning of this talk, there are also other operations that we can define in our tokenizer. The first one is normalization. So we can use directly the Bert normalizer, Or we could redefine the sequence of normalizer. It's the same. Well, it's almost the same. You can check at the course to understand what could be missing here. Then we can define the pre-tokenization operation. We can take the opportunity to see the result on an example. So here you can see that the words have been separated from each other. And now that we have defined all the operations upstream of the model, we can train the model. So to train WordPiece, there are two arguments that are particularly important. There is the special tokens and the vocab size. In the special tokens, we have to list all the special tokens that we want to add to our vocabulary. The vocab size will define the final size of the vocabulary that we want at the end of the training. So we launch the training. Once it's finished, we can define the operations that follow the model. So the next operation is the post-processing. To define our post-processing, we need to know the ID of two special tokens that we want to add to our sequences. So indeed, birds need to add the class token at the beginning of each example, and the separation token between two sentences, and at the end of each example. So once we have retrieved them, we can add them in our template processor. We can also indicate that the output should not contain only the sequence of IDs corresponding to the tokens, but also another sequence indicating the type of each token. Here we will indicate that the tokens belonging to the first sentence should be linked with the type ID of 0 or 1 otherwise. So let's look at what it gives on an example. We can see here the resulting tokens, and we can see that the class token and the set tokens have been added to the final sequence of tokens. We can also look at the type IDs, and the tokens belonging to the first sequence are indeed linked to 0 or 1 otherwise. Finally, to finish our design, we have to tell the decoder that we have used a WordPiece model and that we should gather the tokens starting with 2 hashtags with the previous token. So at this point, we have finished designing our tokenizer, and to be able to use it with the language model, we can load it into a tokenizer fast from the Transformers library. And that's it. It's finished. You have a tokenizer which is ready to be used. So after that, you can see that the notebook shows another example, even another one. So don't hesitate to test it yourself. Of course, in this talk, I did not have the time to deal with everything, but I could simply give you an overview of what you can do with Transformers and Tokenizers libraries. As said at the beginning of this talk, the part 2 of the course has a whole chapter dedicated to the tokenizer, and I really hope that you could find a lot of useful information there in order to get really your own tokenizer. I suggest that we use the remaining time for any question you might have.
Welcome back, and thank you very much for that really nice talk, Lucile. It's very informative, and it's cool to see the kind of inner workings of a tokenizer. So we have a couple of questions. I think you kind of mentioned this a bit in the talk, but it'd be nice to just maybe expand a bit on it. So the first question is, when should I train a tokenizer from scratch? And why can't I just always use one from the Hugging Face Hub?
So you will have more information in the course about this question in particular, but the tokenizer is really something that needs to be adapted both to your data and your model. So you can't use, for example, a tokenizer which is not formatted for your model, and you will see that some tokenizer had additional special tokens. So, for example, so you have to be careful about what is added with the tokenizer. But it also needs to be adapted to the data. For example, you can try different tokenizer on your data. And if you saw that the splitting is really weird, the text is split on really a lot of tokens, it might not be really fitted to your data. Yes, I think the best test to do is to test an English tokenizer. There is a lot of English tokenizer on the app, and test it on a really different language, like for example Hindi, and you will see that it's not the best fit you can find.
And maybe just to ask then a follow-up question is, you said, okay, suppose I have a tokenizer that is not really well adapted to my data set, then it will typically chop it up into like, many subtokens. Why should I worry about this? What's the kind of problem with that?
The first one is you can see with a lot of language model, you have a sequence of a limited length. So for example, BERT, it's 500 on 12. On the most you can find is 248. And so if you take too much tokens to say not much, you will at the end not have a lot of context to give to your models. And it's really something which is great with the transformer models. It's really to use them as much as context as we can in our intention layer. So that's why it can be problematic.
Awesome. And I think another thing that I've experienced is that if you have very long sequences, then you actually also get penalized because attention is usually, a kind of slow computation. So you kind of get two problems. You get one is like you don't get enough information, and two, your training is slower. So this actually raises another question, which is this was for me actually kind of surprising the first time I learned about tokenization. So people say, oh, you train the tokenizer with BERT, and I think this is quite a different beast. So maybe you'd like to tell us a little bit about what that means.
Yes, that's a very, very relevant question. And yes, we are talking about training a tokenizer, but we don't train the tokenizer in the same way we train models. A tokenizer is it's more like a statistical learning, but we need to do some computation over a training data set in order to extract some data that the tokenizer need to use to tokenize a new sentence. So for most of the tokenizer, a tokenizer need to learn a vocabulary, which is the list of tokens that he knows.
Awesome, thanks. That's really informative. We have a question now from Alexia. I'll just put it up here. And they ask, how would you use special tokens to introduce more complicated structures of the data entries? For example, if every entry is a dialogue, then each utterance is often separated by an end of sequence token. What do you
I'm not sure to get exactly where the question is. Is it really a technical question?
Yeah, my understanding of the question is like, we know that we have these special tokens in all these tokenizers. Like, for example, in BERT, there's the CLS token or the SEP token. And this is kind of a choice by, the designers of the models, how they want to encode some information that's like sort of special to indicate, sentence structure or whatever. So the question is like, if you're doing something like biology or law or something, could special tokens help in that context?
In this sense, yes, I think they can definitely help. I'm sorry, I don't have, I think, really a good advice to give on how to use these special tokens. But yes, you can definitely leverage special tokens in order to tell the model that between these two special tokens, it's a question. Between these two special tokens, it's the answer. You can really use the special tokens. the best way to do it technically is to put them in the template processor part of your tokenizer from the tokenizers library.
Awesome. Yeah, and this is actually a kind of related problem. So when you work in industry, you often have like a domain that is quite different from, say, Wikipedia, which is where BERT and all these other models are trained on. And so you get this kind of out of vocab problem where a token maybe doesn't belong in the vocabulary of the tokenizer. I was just wondering, like, how do you think about this problem, and are there some good strategies that we can use to deal with it?
That's a really good question too. One solution to the out of vocabulary problem is to use the byte level tokenizer. So what we'll do a byte level tokenizer is like the very fundamental unit you will use, it's a byte, and we only have 258 values for a byte. So we can definitely store all the values of a byte in our vocabulary. On doing that, we will be able to tokenize any new text we can find afterwards. There is also another solution proposed to this problem, but it's really more at the stage of research, I would say. It's really tokenizer based at the unit level, so the byte. You have byte T5, for example, but that's more really recent tokenizer, and it's not the more common that we can find for our language model.
Cool, thank you very much. That's a really useful tip. Maybe one last question is more personal. So could you tell us a little bit about what work you do in the BigScience project?
Yeah, sure. I will not have the time to really give you the whole view over what BigScience is, but it's really a research project with 700 researchers. So to organize everything, these researchers are working together in working groups. So I'm personally part of 2 of these working groups. For one, I'm mainly helping on the engineering side, so really running big experiments and really big model on a really big supercomputer, which is called Janze. And with another working group, I'm more working on really the design and research sides, and we are really studying one question in order to see if we can improve in a way the training of language models and give them more capabilities.
Cool, thank you. And I think we have a minute left, so maybe I'll ask you one last question. What is your favorite tokenization algorithm and why?
I think it's the unigram LM. I like the probabilistic approach.
Great.
Thanks a lot for your talk and your other answers to the questions.